We're going to be looking at how to solve growth and decay model problems using differential equations. So in our first example, it says that we have a culture that initially has some initial value. We're going to call it P naught, population naught, number of bacteria. After an hour, the number of bacteria is 3/2, or like 1.5 the initial. So whatever our initial is, an hour later, it's increased by 50%. It is now 1.5 the original amount, okay? If the rate of growth is proportional to the number of bacteria P present at time T, that is our key of how we're going to set this up. The rate of growth is proportional to, so rate of growth would be dP dt is proportional to the number of bacteria at any time. Determine the necessary time for the bacteria to triple. So we can solve this one of two ways. My method that I would choose is actually separation of variables. I would move P over with my dP. I would leave K, which is just your constant of proportionality. K is what K is. It depends on the bacteria, the growth rate, those types of things. When I integrate both sides, I end up getting the natural log of the absolute value of P, which we only have positive population, so I'll be able to drop that here in a second, is KT plus C. When I take the natural log, E function of both sides, I end up getting an exponential growth function, which should make sense. If your growth rate is proportional to the population at a certain time, that means that like whatever your growth rate is a multiplier each and every time, okay? You can solve this with a linear method by subtracting Kp to the other side. If we do that, we end up getting that mu is e to the integral of negative k dt. So negative k T is our integral here. In this model, you end up getting the derivative of e to the negative kt p is equal to 0. E to the negative kt times p is some constant. And when I take e to the other side, we get this exact same situation for our population equation, okay? All right, after 1 hour, I know that the initial amount is 3/2. Well, I do know, I'm going to go ahead and change my color so we can do this. I do know initially I have P naught, okay? So at T equals 0, I have this P naught. So let's say this, so C is whatever our initial population is. And so then after 1 hour, I know that I have 3/2 of that. So 3/2 are 1.5 P naught e to the k. These will cancel. I get 3/2 equals e to the k. If I take the natural log of both sides, k is the natural log of 3/2. Let me see here, which ends up being 0.4055. Sorry, I had to check my notes on that one. All right, so what does that mean? That means that my equation here for P must be whatever P naught is, e to the 0.4055t. And then I want to know when the bacteria will triple, right? That's what the question wants. So let's solve this maybe in a different color so that we have a different color here. So 3 P naught. So that way the initial would triple. And now I'm trying to solve this for time. So these would cancel. I would have the natural log of 3 is equal to 0.405t. And then I could divide this over. And I get that that time is going to be about 2.71 hours. All right, so that's an example of exponential growth. Notice our K here ends up being positive. That's because we're taking the natural log when we're solving for K of something bigger than 1. Natural log function looks like as a parent function, natural log of 1 is 0. So when I take the natural log, we're going to be doing that a lot, which is why I bring this up. When I take the natural log of something bigger than 1, I'm going to end up getting that K is positive. If I take the natural log of something between 0 and 1, I'm going to get something that is a negative K. Negative K meaning exponential decay, because e would then be to a negative exponential power. So let's look at an example of that on our next problem here. So there is some kind of reactor that takes relatively stable uranium and puts it into isotope plutonium. After 15 years, it is determined that 0.043% of the initial amount has disintegrated. That is teeny tiny. Hold on one second. 15 years. This is your initial amount, okay, A naught. 15 years later, 0.043% has been disintegrated. So if I take 100% and I subtract out 0.043%, then that means at t equals 15 years that my amount is 99.957% of A naught, okay? Or mathematically, we can write that as 0.99957 times A naught, right? Okay, this has a very, very long lifespan. We're going to try to figure out the half-life of this isotope, okay, if this is the rate of disintegration, so that every 15 years, another 0.043% is taken away. So let's think about what this looks like graphically. Okay, before we even get into the differential equations part, you have this initial amount, and then 15 years later, you have this much, and then this much, and this much. And actually, it's not going to ever go to 0. It's never going to equal 0. It will go to 0. But this is where this exponential decay equation is going to come from. So anytime you have growth rates that represent exponential decay or exponential growth, like we just looked at, then we could say here that dA dt is equal to Ka. And that will always give you that A must be equal to CE to the KT. Now, because this is exponential decay, we're going to find that K is a negative here, which then makes it exponential decay. So let's plug in our initial condition, okay, A naught. We already know that what that means is at time 0, it's that. So A is equal to A naught, e to the KT. Now be careful, because on some of these that we look at, there's going to be a plus or minus constant in the front. That's going to change things. But when it's just CE to the KT, A naught is your C. Okay, and you can plug in t equals 0, solve it, and you can find that. Now I do know that 0.99957 A naught is equal to A naught times e to the 15K. And so if I solve this for K, I'm going to end up having that K is equal to 1/15 times the natural log of 0.99957. Now that's a number inside my argument of my log smaller than 1. That's going to end up being negative, and I'm going to divide that by 15. It is going to be so small, okay? The K that we find is negative 4 zeros, 0.0002867. So that is our constant in which this has exponential decay. Okay, that's our constant of proportionality related to this equation. Okay, so now if I want to figure out half-life, then what I need to do is I need to know, well, when is 1/2 of A naught going to be there, right? And then that's our K. I'm just going to write it as K because it's so small. And we'll plug it in there. So choop, choop. So I'm going to have natural log of 1/2 and then divided by this number, right? So if I take the natural log of both sides, that gets rid of my E. And then if I want to solve this for T, I need to divide that by K. So T there we go, is equal to 1 over this K value, natural log of 1/2. Now K is negative. The natural log of 1/2 is also negative. We need time to be positive, so that's going to be nice. And time is actually 24,180 years. So if we had 100 grams of this to start with, which is not big, it would take 24,000 years to get to 50 grams. That looks like 80 grams, sorry, but 50 grams. That didn't make it any better. Okay, you get the idea. So it takes 24,000 years, y'all, to get to 50 grams. And then here's the thing of half-life. In my brain, I'm always like, oh, well, then in another 24,000 years, it's gone. No. In another 24,000 years, we still have 25 grams left. That's how half-life works. And that's why it's exponential decay, not linear decay, because it's still only half left every 24,000 years. So then in another 24,000 years, you have 12.5 grams left. Like it never ends up going away, which is why chemicals like this are really kind of terrible and dangerous. But that is how we're going to solve exponential growth and decay models using differential equations and then plugging in additional conditions to solve for the particular solutions for that situation.